Okay, welcome back. So this is the second part of lecture 9. So in this part I want to talk about um, the speed of electromagnetic waves, and also reflection and refraction, right? So this is maybe the middle part of the lecture. Okay, so I like thinking about waves and wave speed um, by repeating mantras about waves, right? So this is something that is universally true of waves, that the speed of the wave depends on the medium. And the way that I like to remember this is to think about um, uh, the the different kinds of effects of running on wet sand versus dry sand. I used to live in San Diego and I love jogging, and so there's a huge difference between wet sand and dry sand, what it feels like to run on it, and how fast you can go when you're running. And so I would always look at the tides and the prediction for the tides to plan out when I wanted to do my runs on the beach. A nice problem to have. So this is what I think about when I think about wave speed. That the speed is determined by the medium through which we're trying to transfer this wave, right? So one example of this is like a guitar string, or a violin, or any kind of stringed instrument. So one thing that you can do with a stringed instrument is actually tighten up the pegs and increase the tension in the string. So that actually has the impact of changing the speed of a wave on a string. So when it's tighter, the speed of the wave is faster, right? And changing the speed of the wave on an instrument actually has an impact on the frequency that's created when you excite that string. So here's another mantra that I have about waves. It's that the frequency of a wave depends on the source, right? So in terms of this wave, traveling on a slinky, we have these two different examples of the types of waves that you can create with a slinky. The woman who's creating the wave, she's determining the frequency of that oscillation. How could she change the speed of the wave? The only way to do that would be to somehow change the slinky itself by either increasing the tension or decreasing the tension. So I would expect she could stretch out the slinky. That would increase the speed of the wave. She could also compact the slinky, and she would probably see the wave moving slower, right? So the frequency depends on the origin of the wave, whatever's creating the wave. The speed will be determined by the medium itself. Ooh, I have little animated graphics to represent transverse and longitudinal waves. Frequency only depends on the source. Here's a quick clicker question to see if you're paying attention. What velocity do radio waves travel? And hopefully you said the speed of light, right? Because radio waves are electromagnetic waves. Okay, this is a demonstration which I don't expect everyone to follow. It's a calculation of the speed of a wave. The only thing that I hope that you get out of this is that the speed of light can be calculated directly from Maxwell's equations. So if you remember, we've been spending all semester talking about electric fields and magnetic fields. We had one rule about how electric fields are created from charges. We call that Gauss's law. We had a rule about how magnetic fields are created from currents. We called that Ampere's law. We had a rule that the total magnetic flux from a surface has to be equals to 0. That's actually a law that doesn't really have a name, but people call it the no monopole law. And then we have Faraday's law, which tells us that the change in magnetic flux is equal to the EMF that's generated, and EMF here is written as electric field, the integral of electric field, right? So this is a compendium of all of the laws that we've learned about in electromagnetism, and this is actually an alternative way of writing the same thing. So a lot of times you'll see Maxwell's equations written like on a t-shirt or a tote bag or something. So more often than not, you'll see it written in this different form. So this is actually the integral form of Maxwell's equations. This is the differential form of Maxwell's equations. And this is a derivation where you can calculate the speed of light. And so it's actually a combination of using Faraday's law and Gauss's law together to get something that we call a wave equation. So this is a second derivative of electric field with respect to x, and this is a second derivative of electric field with respect to time. And then the end goal here is this combination of constants here. So it turns out that whatever constant fits in to this double partial differential equation, you can use it to derive the speed, right? So actually the square root of the inverse of whatever fits here is the speed of a wave. And in this situation, we can calculate the speed of an electromagnetic wave in a vacuum. It's actually equal to 1 divided by mu naught and epsilon naught. So remember, mu naught and epsilon naught, these are the permittivity and the what's the other one? Sorry, I've forgotten. It's blanking in my mind what epsilon naught and mu naught are called. Anyways, they're specific properties of a vacuum, right? So mu naught is more associated with magnetic fields in a vacuum. Epsilon naught is more associated with electric fields in a vacuum. But combining them together, we get the speed of light 3 times 10 to the 8. Okay, so now next part of this derivation is actually what happens if you have Maxwell's equations not in a vacuum, but in matter, right? And so, I wrote what mu naught and epsilon naught are. So mu naught is called the permeability of free space. Epsilon naught is the permittivity of free space. In matter, you have different constants, mu and epsilon, that tell you what is the ability of magnetic fields to be in a certain material that we would call the permeability, mu. And also what is the ability to have electric fields in matter, we would call that the permittivity, epsilon, right? So this subscript 0, this is really only for a vacuum, whereas the more general version, permeability and permittivity, these are for any material. So if you redo that process of calculating the speed of an electromagnetic wave in matter, you get something which is, instead of in terms of mu naught and epsilon naught, it's actually just mu and epsilon. So we can rewrite this speed, the speed of light in any kind of material, v. Let's write it in terms of the speed of light c, and a new constant n. And so n is going to be called index of refraction. And it has a formula, so it's going to be the ratio of the square root of mu naught epsilon naught divided by the square root mu epsilon divided by the square root of mu naught epsilon naught, right? So it's some combination of constants. Mu and epsilon are for a particular material. Mu naught and epsilon naught are for a vacuum, right? So what values can n take? So first of all, n is dimensionless. And secondly, it's always going to be bigger than 1, right? So imagine if n was bigger than 1, we know that v always has to be smaller than c. And that is indeed true, that the fastest speed that waves can travel, or electromagnetic waves can travel, would be in a vacuum. Whenever light travels through transparent material that is not a vacuum, we actually need to use this index of refraction n. So notice that in a vacuum n is just 1, obviously, but in air it's slightly more than 1. And then these are maybe the most important values that we want to know. The index of refraction in water is 1.3, and then a typical glass has an index of refraction of 1.5, right? And so these numbers, 1.3, 1.5, they tell us the relative speed, how to compare the speed of light to the speed of light in a material. Sorry, the speed of light in a vacuum to the speed of light in material. Okay, so I have here a table to compare and contrast sound versus light. So remember, both sound and light are waves. Sound waves are created by molecules in a medium that are disturbing each other. So we have a pressure wave of molecules. So we have, dense periodic patterns of dense and non-dense waves of material creating a sound wave. For light waves, we have oscillating electric and magnetic fields, or we can think of them in terms of photons, right? For sound wave, a medium is required, right? So I definitely cannot have a sound wave in a vacuum, right? So this is, why they say like, oh, if you scream in outer space, no one can hear you. It's because there is nothing to transfer sound when you're in a vacuum. For electromagnetic waves, a medium is not required, right? We can have waves in a vacuum. We can have light waves in a vacuum. Okay, so what is the relative speed in different materials? So in a vacuum, you don't have any sound. In air or gases, sound travels slower than it does in liquids and solids. And as I heat up material, sound waves travel faster in hot material versus cold. Okay, and then actually the reverse is true for electromagnetic waves. So in a vacuum, light travels the fastest. In air, it travels slower. And then in solids and liquids, it travels slower than it does in gases. Okay, so let's continue talking about index of refraction, n. So once again, speed depends on the medium, right? So n is a property of the medium that you're transferring electromagnetic waves. And so this is a demonstration of what would happen if I had light going from one medium to another. Okay? So here I have light, let's say it's traveling from top to bottom. So I have a wave. In medium 1, I have an index of refraction N1. I have wavelength lambda 1. And then in medium 2, I have an index of refraction N2 because light travels at a speed v2. And then I have wavelength lambda 2. So what is conserved when I go from medium 1 to medium 2? So remember my two mantras, that speed depends on the medium, frequency depends on the source. And specifically, I would expect that the frequency F1 has to be equal to the frequency F2. And the reason for this is essentially because the energy of a wave, at least in the photon perspective, is proportional to frequency. And so if I want energy to be conserved, going from medium 1 to medium 2, I would expect F1 to be equal to F2. Okay, so then if the velocity and the wavelength and the frequency are related by that formula, that V wave is equal to frequency times wavelength, and I can see here that the wavelength lambda 1 is bigger than lambda 2, how would I expect to relate V1 and V2? So where is the light traveling faster? In medium 1 or medium 2? Okay, hopefully you've figured out that if the frequency is the same in F1 and F2, then I have lambda and speed being proportional to each other. So here I have lambda 1 is bigger. I would expect V1 to be bigger than V2. Okay, so what stays the same? Energy is conserved. Frequency, right, has to be the same. What changes? If the material has different index of refraction, that means that the speed would be different. And then the wavelength also would change in relation to that, because wavelength and velocity are proportional. Okay, so then here are some formulas to relate how the wavelength, how we would expect the wavelength to change and how we would expect the speed to change. So we know that F1 is equal to F2 because the frequency is conserved and energy is conserved. We know that c is a constant, the speed of light, and so that means that we know that the velocity times the index of refraction, v times n, has to be a constant. So I would expect v1 times n1 to be equal to v2 times n2. And then I also know that v is equal to lambda f, right? And so I could replace here, instead of v1, I could replace v1 with lambda 1 times f1, right? But then I could drop f from both sides and just get lambda 1 times n1 is equal to lambda 2 times n2. Okay, so now that I know that here lambda 1 is bigger than lambda 2, I would expect v1 to be bigger than v2. How would I expect n1 to compare to n2? So it would be the opposite, right? n2 is probably bigger than n1 in this case. Okay, so here's an example problem. So go ahead and try this problem out and then check back to see if you get the right answer. Okay, if you're coming back, let's work through this problem together. So it says I have blue light of frequency given here. It's traveling in water and reaches a glass surface. What wavelength does this light have inside glass? So assume that water has an index of refraction 1.3, glass has an index of refraction 1.5. Okay, so I think there's more information here than we need. we can figure out actually the wavelength of light using this formula. So I know that here the speed of light in glass is going to be 3 times 10 to the 8 divided by 1.5. So what's 3 divided by 1.5? It's 2, or 0.2. So 0.2 times 10 to the 7. And then I could divide that value by the frequency to get the wavelength. So it's 0.2 times 10 to the 7 divided by 6 times 10 to the 14. So I think it's going to be B. Let's try. Ooh, I was wrong. Okay, so hopefully you got A. Is the wavelength of light longer or in water or longer in glass? Okay, so I know that the index of refraction of light is bigger in glass, right? So I would expect the wavelength to be bigger in water, right? Good. So you could figure this out with the formula that I showed before. N1 lambda 1 is equal to N2 lambda 2, right? So if N is bigger in glass, I would expect lambda wavelength to be bigger in water. Okay, so the next step is talking about reflection and refraction. So definitely with these types of problems, we want to consider light in terms of a ray, right? So with that respect, right, we want to assume that light travels in straight lines, right? So anytime we draw the path of a light, we would use kind of a ruler to make sure that our line is straight. And when is this kind of approximation valid, right? So in terms of thinking about how light interacts with matter, we would say that the ray approximation of light is valid whenever light is interacting with objects that are larger than its wavelength, right? So definitely things will be much different whenever light is interacting with matter that is on the same size, same order of size as its wavelength. But in this case, whenever light is interacting with matter that is much, much larger than its wavelength, we can make this ray approximation of light and basically just treat light as if it's a particle, essentially, right? So a particle that is traveling in a straight line and is not under the force of gravity, right? Okay. So here's some demonstrations of what ray diagrams look like. So here on the right, we're showing the basic setup for reflection and refraction. So reflection would be, if I'm starting this beam off, I would expect to see an incident ray. So I would call ray 1 an incident light beam. Incident. Ray 2 would be the reflected beam. And then what would this beam 3 be? This would be called the refracted beam, right? So light, when it reflects off of a surface, behaves in a certain way. Light that transfers into or out of a different material, we would call that the refracted beam. Another thing that we'll be talking about is the creation of images. So we're going to see that light bends whenever it moves from one material to another. But one thing that's really interesting is that our eyes don't really understand that light can bend, and therefore our eyes interpret images to be directly straight ahead, right? So following the path of a light beam. And so here we have a lifeguard on the edge of a pool. We have a scuba diver inside the pool. So even though these are the real objects, the scuba diver and the lifeguard, because this light is bending, the lifeguard assumes that there's a scuba diver at this location. The scuba diver assumes that there's a lifeguard at this location. So we can come up with the location of virtual images by taking real beams and then back tracing behind to identify the location of where the light appears to originate from. Okay, so these are some things to look forward to that we'll discuss. Okay, this slide is some review of some math. The first thing to mention is just the terminology of the word normal. So normal is a synonym for perpendicular. So a lot of times whenever you hear the word normal, you should think of perpendicular. So here we have a picture of a line that is normal to a plane. Here we have a line that's normal to a line, so perpendicular to a line. Here's a line that's perpendicular to a surface, right, in 3D. Another thing is that there's a lot of geometry involved with ray tracing and reflection and refraction. So here's some review of some geometrical things to know about lines, intersecting lines. So if you remember, there's this process of if I have two intersecting lines, this angle should be equal to this angle, and this angle is equal to this angle. We know that the sum of the angles summing up to a straight line have to equal 180 degrees. We also know the sum of the angles in a triangle have to equal 180 degrees, right? Okay, so good things to remember. I'll remind you of more geometrical things as we go along. Okay, so incident ray. So an incident ray would be the starting light ray whose path that we follow. The angle that an incident ray makes with the normal to a surface we'll call the angle of incidence, right? And so we have either reflection or refraction. So reflection would happen when light hits a boundary and then moves backwards. Refraction would happen whenever light hits a boundary and proceeds into the new medium, right? And so you can definitely have both reflection and refraction happen at the same time. Okay, so now into the laws. So the laws of reflection, so the law of reflection would be that the angle of incidence is equal to the angle of reflection. So here it's really important how we define the angle of incidence. So here I have an incident ray. It's always going to be defined with an angle relative to the perpendicular to the surface. So this would be the angle of incidence. It's going to bounce off in the other direction according to this angle, the angle of reflection, right? And so this law just tells you that these two angles have to be equal. And this would be exactly what would happen if you were playing pool or bouncing a ball off of a wall. You would expect that the angle that you throw an object is going to be the same as the angle that it gets reflected back. Okay, so now let's talk about law of refraction. And actually law of refraction has a special name, But before we talk about light, I really like doing this analogy to light, which is talking about people running on a beach. So it's saying I have a bunch of runners, and they're on a parking lot at point P. They want to get to, let's say, a barbecue on the beach at point Q, and they each pick a different path, A, B, C, D, E. So it's much faster to run on a parking lot than it is in running in loose sand. So which path would take the least amount of time? So maybe think about this for a second. Who would get there first? Okay, so you're probably thinking to yourself, don't I want to maximize the time that I spend on the parking lot? So I probably want either D or E, right? And that definitely makes sense, right? Because I want most of the path to be in the part where I can go faster. And that's definitely true. But consider that maybe path E is just a much longer path, right? And so there might be a trade-off between decreasing the path length, right? So the shortest path length is actually C. C is the shortest distance between these two. And definitely if this was all parking lot or all sand, C would be the fastest path. But because part of it is in the parking lot, part of it is in the sand, we need to balance the trade-off of increasing the path length and also increasing the amount of time in the parking lot. And so I would expect path E would only be appropriate if the speed of running in sand is actually much, 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 much slower than the speed in the parking lot, right? But if it's not much, much slower and is just a little bit slower, then maybe the most reasonable option is D, right? Okay, so what does this have to do with light? So we have this principle, it's called Fermat's principle, and it tells you that light will always pick the path of least time to go from point P to point Q, right? And it sounds so mysterious, right? Like, how does light know which path is the shortest? It just happens, right? And it's really a really cool principle. So the law of refraction, I told you, has a special name. It's called Snell's law. Sorry. I'm going to move my head here. So Snell's law tells me how much light bends at this interface between a slower medium and a faster medium. So whenever I go from a fast medium to a slow medium, I would expect the light to bend towards the normal. Whenever I go from slow to fast, I would expect light to bend away from the normal. Okay, so here's a little animation to demonstrate the same thing. So now instead of having runners running on their own, imagine that they're going side by side in kind of a parade fashion. So what's happening whenever they're walking together is because they're walking side by side, do you see that right when they hit this interface between pavement and mud, there's a period of time when the guy on the right is traveling slower than the guy on the left, like right here, right at the interface. And just during that time, the guy on the left is moving faster and basically pivots closer to the normal, right? So this is maybe another explanation for why light beams bend, is that part of the light beam bends or enters the different material before the other. And that causes the entire row of the parade to shift at an angle, right? And so now we see, okay, we're going from fast to slow. So when we're going from fast to slow, the parade bends towards the normal, right? Here's another demonstration of the same thing, right? So part of the light beam actually hits the faster medium, or the slower medium first, and that's what causes it to bend towards the normal. Okay, and this finally is Snell's law. So Snell's law says that if we know the index of refraction, N1 and N2, in the two materials, we can calculate the angle of incidence, theta 1, and the angle of refraction, theta 2, right? So I can figure out what would be the relative theta 1 and theta 2 given N1 and N2. Right, so if you knew 3 of these variables, you could calculate the 4th, right? Okay, so here's an example. I know the angle of incidence, and I know the angle of refraction. I am told that this laser beam is starting in air, and then it's reflecting and refracting off of a surface of a liquid, right? So I could calculate the index of refraction of the liquid by saying that N1 is the index of refraction in air, which is just 1. Theta 1 would be this angle of incidence. Theta 2 would be this angle of refraction. I could calculate N2. Okay, so here's a demonstration of that. Okay, light incident on a surface makes an angle of 90 degrees with the surface. Which angle shows the path of the transmitted light ray? Okay, so now it's saying we're starting off with this light in red. What would be the refracted light? Okay, hopefully you agree that it should be light ray B, right? Because in this case, theta 1 is just 90 degrees. So no matter what N1 is or N2 is, I would expect the sine of 90 is just equal to 1. Sorry. Sine of 90 is 1. Oh, sorry. This is where this problem is confusing. So it's saying it's making an angle of 90 degrees with the surface. So what would be the angle of incidence in this case? So remember, angle of incidence is defined relative to the normal. So here, theta 1 would just be 0, right? And so no matter what N1 is or N2 is, theta 2 would also be 0. And so that's why you would assume that B is the only option, is because it would not be able to bend. Okay, which of these 3 drawings show a physically possible refraction? So remember, when we go from fast to slow, we bend towards the normal. When we go from slow to fast, we bend away from the normal. Okay, so I'll give you some time to think about this, or you should just pause. Okay, hopefully you're done pausing if you wanted to. So let's analyze situation A. So in A, the beam is going from fast to slow, right? Fast to slow, excuse me, fast to slow, you would bend away from the normal. So I'm saying that situation A is not physically possible. Okay, maybe you want to do the other ones yourself. Okay, so situation B is also going fast to slow, but notice how this refraction is actually changing direction. So that is not something we would expect, right? So we would expect that the refracted ray would actually be continuing in the same direction as this initial ray, but it would be at an angle, probably a different angle from the normal as this one, but this one goes backwards. So this is actually wrong entirely, right? Here I'm going from fast to slow, and I'm bending away from the normal. So fast to slow, I'm supposed to bend towards the normal. So I think none of these. Oh, I guess, okay, sorry, I guess I did this first one wrong. Okay, so fast to slow, bend towards the normal. This one is actually appropriate. Okay. So one last thing to talk about for refraction is this really cool principle, which is called total internal reflection. And it comes from the principle we were just talking about, that whenever you go from a slow material to a fast material, you need to bend away from the normal. So here, this diagram is kind of showing this process with increasing angle of incidence. So here I'm just pointing straight up, so the angle of incidence is 0. Here I'm at an angle of 15 degrees, 30 degrees, 45 degrees. And notice that when the angle of incidence is 15, the angle of refraction here is 20, right? Because it has to bend away from the normal. Here, when the angle of incidence is 30, the angle of refraction is 42. 42 is bigger than 30. 70 is bigger than 45. But here's the thing. Eventually, this angle of refraction hits the boundary before this angle of incidence hits the boundary, right? Because it's always bending ahead, right? Away from the normal. And so there's a specific value of theta. There's a specific angle of incidence where we call this the critical theta, where all of the light would be refracted at, it actually doesn't get refracted at all, right? That it just barely does not get refracted, right? So it's the angle where it's this critical angle of incidence is the angle where the refracted angle theta 2 is actually equal to 90 degrees, right? So here, let me demonstrate it further. So if I start steep, theta 1 is smaller than theta 2, right? Because I'm bending away from the normal. If I go past the critical angle with this blue ray, then I only have a reflected ray, right? Because I would have no refraction. So the red beam represents the boundary of if I have any angle that's steeper or smaller than theta critical, I would get refraction. If I have any angle that is bigger than theta critical, I would get no refraction, right? So it's the critical value of an angle where I still get light to exit the surface, right? At any shallower angle, all of the light gets trapped inside the glass, right? So the reason why this is important is it's the principle behind fiber optics. So anytime I have fiber optics or any kind of situation where I need a flexible tube for a camera, so for endoscopes or colonoscopies, I need some kind of camera that I can place on a flexible tube. So in order to do this, the way that they set it up is that they have two materials. one would be the core material, and then the surrounding that core is a cladding. So in this situation, I would just want to set up an index of refraction for the cladding that is lower than the index of refraction in the core. And then I would want to make sure that any light that is entering this tube is at a shallow enough angle that it's beyond the critical angle. So if it's more steep than the critical angle, you would get light in the cladding. If it's less steep, then all of the light gets trapped inside the core, right? So here's another GIF. It's showing, okay, you could actually have a twisty tube where light actually gets trapped in that tube. This is a demo. And in this demo, all you need is a bucket of water, and you poke a hole in the bottom of the bucket so that you have a stream of water. And we know the index of refraction of water is higher than the index of refraction of light. So if you trapped a laser beam inside this flow of water, you would just have reflections of light within the water. It would not be able to escape the water. So that's what's happening here in this demo. Okay, so how could we calculate this critical angle? So here I'm just using Snell's law, but I want the angle of refraction to be 90 degrees, or here I just wrote it as pi/2. And what's the sine of 90 degrees? It's 1, right? So you could use this to solve for the critical angle, right? Because I have n1 sine of theta critical is just equal to n2. And then I can solve this equation for theta critical. Okay. So I think I'm going to pause here, stop, and then I'll continue, and then we'll talk about ray tracing. Okay.